So our first test is going to be next Tuesday. Then we'll have a test in for when you do your mission grades. It's just going to be on the special election and stuff. So up through like the team you knew, things like this. That things like this. And I'll get up to stuff like that. I'll give you a review, Joe. None of the stuff dealing with, we started doing parallel transport last time. Then we get the derivation for the Christopher symbols today. None of that is going to be in there. That'll be all in the second test. So the second test will have a lot of the mathematics connected with those stuff. Okay. So that said, let's actually start calculating these ones here. So what I want to do is, let's just remember what we did last week. So y is the derivative here, not y doesn't. That have good transformation properties. So first of all, let's make sure we even understand what it means to have good transformation properties. If this has good transformation properties, what do we want?
Should transform like Lorentz.
Okay, so this part, so in other words, if this is good, by good we mean.
Oh, the one part transforms like a covariant, and the other transforms as a contravariant.
Yeah, so this is good. If I had this guy here, what should this be? Well, I have this alpha here, I have this beta here, I have these x's like this. You decorate for me. Again, when you do these, it's just deal with one index at a time. So let's do the new index first. So just at the new index, let's forget all about that mu. But I just said the new index, how to decorate that. Let's remember this for a minute. I just gave you, cover this up. It's all veiled. I just give you that on that transform.
The new up top and beta on bottom.
Now there has to be a prime someplace. Where's the prime go? On the top. Why? Because that's when we worked it out. That's how all those went. We set them all. Now, then what about this one? Okay, where's the prime go? It's always the opposite one. This is going to go down here. This is the prime. Now, decorate it for me.
Mu on bottom, alpha on top.
Yeah, on the bottom, alpha on the top. So the question, this is what it means to have good transformation properties. Now the question is, does this have good transformation properties? And it didn't. And formally, why was that? Because we know this. So let's write this down. So this would be this. Using beta. So we have that. Now, then if I take the mute derivatives, but that's going to be the same thing as this, which is this. What does that give rise to? Product rule, Reggie. You have trial here. And we rewrote this one. How did we rewrite that? So this is the same thing. As this. So if we put that together. Get our here. That, and we get then this guy over here. So this part is good. This is good. So we want this. It is not. So the derivative of a contravariant vector does not transform as you'd like. Now, fundamentally, what caused that? And how did we fix it? So where do we say the technical problems? This technical problems going to also fix it. Close, very close. So remember what we have here. We had a point here. Call this x. Call this x plus delta x. Again, this right here is collected for all the indices. This is basically this is the x0, x1, x2, x3. Same as this. We had a vector here like this. Well, this we knew this is x. And then we move that vector over to here, it becomes this x. This times x. Now, what does a derivative involve?
Slope.
It is a slope, but in terms of words or mathematical expressions, it's this point minus this point. So if I wanted the derivative here, if I needed this stuff to be new, what did we do? It's gonna have to be this value here. Minus this value here. Now, why does the problem, that's right where the problem occurred at a fundamental level. Now, why does that already mess things up?
There's there's more than one.
It's a little more basic, right? If I have this, I'm gonna put from some things. What is this? I'll just call some. If I have this guy here is gonna be this x prime alpha, x new, be new here. And then likewise here, I'm gonna have this here. Now, what's the technical problem? Where is this evaluated at? And where is this evaluated at? This is evaluated at the point.
X plus delta.
This is evaluated at x plus delta x. This is evaluated at the point. Just as. Can you then factor out this term here? You can't factor this out. These are not the same. It can't be pulled out. So that's at a fundamental level where the problem came from. But these two factors here are evaluated at different points. So how did we fix the problem? we came up with something new.
Parallel trains.
So we introduced the whole idea of parallel transport. So we introduced. The idea of parallel transporting. V new and X to V new and X and stuff to X. So if I redraw that picture, this is X, this is X plus delta X. And this is my buddy V new and X. Here's my change factor. So somehow we're going to take this vector and we're going to move it over to here. And we call this V new parallel. And then what I can do is I can take the difference between these two vectors here. So I'm going to call this delta V new parallel. And this is going to be by definition V new at X plus delta X, just like before. But now we're going to subtract the parallel transported version of this V new to here. Now these are evaluated at the same point. These are both evaluated. And X will stop X. Now I can factor out that term, my life is going to be good. How do we go about doing this? We needed a way of figuring out what this V parallel is. So what was V parallel new? So it's going to be the original vector plus some change. I think we call it delta. We want delta. So we call this delta V parallel. And how do we take this to be? We define that to be linear in the displacement and in the components of the vector. And so we put a minus sign there. And why did we put a minus sign there? Actually, that's the answer. This is just entirely conventional. This is just by conventional. Well, we did it first, came up with that. So usually if you see a minus sign coming in for no reason, why is it introduced? Probably to get rid of it. So chances are you're putting in a minus sign so something else becomes positive. Because if you can avoid a minus sign, people like to avoid a minus sign. So that's probably the origin of that, although I don't know that for a fact. And we're going to assume it's linear in the displacement. So it's going to be some delta X here, and then V here, we need components, and so I'm going to put an alpha here, and I'm going to beta there. So this, whatever this is, should be linear in these two here. And then what do we call the constant of proportionality? And again, it's not a constant, it's going to be constant at that point. But
Gamma.
Gamma. Hey, that looks familiar. We have to sum over all the alpha and beta values, so we should go here and where alpha and beta on the bottom. Okay. Hey, then what's gonna have to be on top then?
New.
It's gonna have to be in here. I guess I should put it because that's the next component. And then if you put this all in here, you get this delta V parallel new equals V X plus delta X minus V new of X minus this gamma new. Oh, I'm good. Delta beta, delta X alpha, V beta, like that. We rewrote this. Minus minus become plus. And then we did one other thing. We divided this by some direction here, some component, let's say delta X mu. I guess I should be. I cannot be entirely consistent here. Okay, that is kind of bad notation. I'll put a delta here. Okay. Mind if I just scratch this delta up here? Capital delta. I apologize for that. Okay, let me tell me when you fix your notes.
I think you did do it like that last.
Like this?
Yeah. So I had in mind.
But I mean, it was bad that I was switching my note. The bad notation was referring to what I was doing now. Because I mean, I put two different uses of delta. So bad today, not bad on Friday.
So that capital delta X is different from the lowercase delta X and the D.
Which place?
There.
Yeah, not really consistent. Well, this should be a delta X here. This should be a delta X here.
Okay.
This should be a delta X here. That should be a delta X here. Sorry about that. Let me know when you have my screw up patched up. Oops, there's two others to that. So there should be a delta X. There should be a delta X.
It was just always.
Yeah. Change all the little deltas to capital deltas.
Or would you do that on the?
Yeah, well, this one I can call this one. I'm going to call this one here because the distinction from this guy here because they actually are different. That one. Okay. Everyone patch up my mistake? Okay. So what does that get us? We're going to take then the limit. This delta X nu goes to 0. And this guy here. We define this to be the covariant derivative here. That. And that was by definition by that equals what? This guy here becomes what? That's just the original definition of
Derivative.
what kind of derivative?
Partial.
It's just a standard partial derivative. So this is just our partial derivative of the respect of partial derivative of v nu in the mute direction. Then what do we say about this guy here? Delta x alpha, delta x mu, that becomes then this guy. And that has a name. Oh, this is a mu. That's what we can.
Delta.
That's our Kronecker delta. Okay, so this is our delta alpha mu. And so this means that our covariant derivative is this guy here. With mu beta. Okay, so this is now the second way of using this. Before we were taking derivatives of unit vectors, and then we had to write those in terms of soft symbols, and now this is another way to do that.
Why did that go away? Oh, never mind.
Good. That makes sense. Now we wanted some properties here. Oh, so we said we would like this to obey some nice properties. What were the nice properties?
It should not change a scalar.
Tinker with that.
You apply it to the scalar.
So one of them was, I take the mute derivative. This is a Lorentz scalar. Okay, what did we want that to be? We know that if I have a vector here, right? I have a vector component here. But if I have a phi here, what would be the beta component of phi? It doesn't exist. So what would you want this to become? Your life can become just that. That's one property. What else did we want? So if we have this, what would we like?
Product rule.
We want the product rule. We want it to be this. So we want that. Then there's another property too we wanted. Instead if we had this. I had that. That's the same thing as that. What would you do with this thing?
Product rule.
Product rule. So that'd be this. And we wanted something here. We wanted to tilt it. We don't want this from here. We basically want this derivative here, just act on the contour component here, and then just end up with this. So how do we end up with this? So we want this. Equal this. We don't want this term. So what did we have to say? That this right here has to be? Has to be 0. We gave that a fancy schmancy name that was called. This guy here. This is called metric compatibility. Yeah, it's going to become extremely helpful for us. So here was one other very calculating about yourself and something. Okay, so I get one thing before we actually get with the Christoffel solution. So let's say we know that this we know this is true. The question is, what is what happens if instead of having a contrariant four vector, we have a covariant four vector? Okay, and I'm gonna give you what the answer is, then I'm gonna prove it. The answer is gonna be this guy here. You lose this. And then minus, we're gonna have, let's say, alpha here, and then there, and be alpha there. And the derivation of this is Q. And the proof comes from this. I'm gonna call phi, I'm gonna call phi to be this. Right. If I take a contrariant four vector and knot it into a covariant four vector, I'm left with a scale under general coordinate transformation. So now let's take then the newt. Okay, since I have news, do you mind if I'm gonna change this to the else? Just so I don't have to change my notation. Sorry. I can take the mute covariant for this. Okay, so what does that have to equal with? What property did we want here? Product rule. So this has to equal this. But it has to equal something else too.
The partial mu of E.
Yeah, this right here is a Lorentz. This is a scalar under a general coordinate transformation. So this has to be the same thing as this. All right. Can't be any different from that. This has to go up. Well, over here, this is my partial mu a nu. Means b nu. Plus my it's my gamma mu nu alpha a alpha. B nu, and then over here. Oh, I can't even go further. Yep. Okay, so what is this guy here? This guy here gives me partial mu a nu b nu plus a nu partial mu b nu. Distribute through to my friend here. What next thing happens?
The a new covariant derivative of these mu.
Now covariant derivative here, this regular partial, that term
Oh,
cancels that term. So you're gonna take this to this side here. Oh, yell at me. What happened when I went to here? I dropped it new. It should be new here. I can factor out this A, what I can do here is I want to pull out an A new here. If I pull out an A new here, what do I have to do? I have to change this A to A, this alpha to A new. I have a new here. So what do I have to do?
Reverse.
And is this term right here, I'm gonna have to take my new, my alpha, and exchange them. Well, my A new here like this. Now, what did assumption did I make about the vector A? Give me anything, right? A new is arbitrary. I can make that anything I want it to be. That'll always work. Therefore, the only way to have this always work is what? Is that if this fellow here equals this fellow. Therefore,
Is that not just the same as canceling it? Or
can't cancel, how come?
It's the matrix.
This is so. Well, there's a summation of terms here. And that's how they don't cancel. Okay. Pretty slow. Pretty proof. Any questions on that? There's a couple more things, then we can start doing a lot of things with these. If all goes well, by the end of the week, we'll have the rebound from the true tensor. If not, we'll certainly have it before break starts. We'll have all the main pieces of relativity before break. Okay, now let's actually calculate the Christoffel symbols. And how can we calculate the Christoffel symbol? Okay, I'm going to give you the answer to the proof. The proof is be very careful where you put indices. The answer is going to be this. If I have mu alpha beta, it'll be 1/2 G mu sigma. Partial alpha G beta sigma plus partial beta G alpha sigma minus partial sigma G. Notice gamma is symmetric in the lower indices. So that's nice because that means if I have alpha beta here, since it's symmetric, this has to be beta alpha here. And then have it, the alpha beta here, because basically your G is always symmetric. So that's how you're going to calculate these things. The question is, why does that work? So now what I do is do the proof. Proof. This is true. Ready? It's going to be a lot. This is going to look very similar to first semester. This is going to look very similar to classical mechanics. The question is, how do we complicate the world line S? What do we know about DS? Yes. In our general coordinate transformation, how can we write that always?
Negative CT squared.
That's Cartesian. I mean that's for flat space time. G mu nu dx nu dx mu dx nu. And what is that?
Does that make sense?
Let's go do the argument again. Okay.
Thumbs on all the things, you know.
The ds squared is this ds vector, not ds vector. And how did we write these? We wrote this as dx mu e mu vector dotted into dx mu e mu like this. We wrote this as dx mu e mu dotted e nu. And this term right here is by definition. That's what G mu. Okay. That's the fancy name for G mu nu. Whereas eta, when it's eta is what?
Flat.
The flat space-time metric tensor. It's not necessarily flat space-time, it's just the metric tensor. So this right here, this is just your metric tensor. That makes sense. Okay, so I'm going to take the square root of that. And I say ds. This is the square root of this guy here. Okay. And what I want to do is, so I want to integrate this thing somehow. The question is, what are we going to integrate on? So if I look at my CT here, let's just go to this flat space time. Here's X. And so let's say here's my little path like this. So this whole length here, that's my S. And so I need some parameter to basically integrate along here. So what might be a good parameter to integrate along there? Well, it's going to be the proper time. Why would I use the proper time? Because the proper time is a
Lorentz scale.
Lorentz scalar. So what I'm going to do is I'm going to specify basically any point along here in terms of tau. So I'm gonna go up here. I'm gonna write this as, I'm gonna put a detail on the top, detail on the bottom. I can take the detail on the side here. And that gives me this detail. Square root of G mu nu, and that can emphasis dx mu, detail, dx mu, detail. This is my ds. So my s is going to be the integral from some tau initial to tau final. ds or this guy here. Okay. Does that make sense? Now I want to find the geodesic for this. What is the geodesic? Or this world one. What did the geodesic? This is a geodesic. If I take a variation in it, here, or variation like that, this is a geodesic. What do you think the variation is going to be? That this is going to be an extreme. The geodesic is going to mean that if I look at any variation on this, I get 0. So the geodesic means the variations in this are 0. Okay, now if you have a sphere, what are the geodesics for a sphere? I'll give you a globe right here. Not the geodesics, what are they? The great circles. Okay. Everyone's happy with great circles? Sphere. Great circles are
The biggest.
basically the biggest ones along. They're not this like that. They're this guy, or this guy, this guy, or this guy. Basically, take the equator and kind of move it anywhere you want, like this. So like that. That's a great circle. That'd be the geodesics. Okay. When we do that, it turns out that this Christoffel symbol is going to pop up naturally. Okay, does that make sense what we're going to do?
What are we doing with the geodesic?
Well, we're going to actually, this is our S. Now I want to find the geodesic for. And when we do that, we're automatically going to get that geodesic. We're going to get that Christoffel symbol. Because we're going to end up with the geodesic equation, which is going to be one of the main equations for relativity, general relativity. And it's basically going to have that Christoffel symbol. So that Christoffel symbol is going to be intimately connected with geodesics. Okay. Just so you know, we're going to have kind of it's going to be a frustrating class today because the derivation is going to stop midstream. Because it turns out that I cannot do this in 5 minutes. I don't want to do, plus I don't want to rush it because it's going to be notorious with indices. But at least let's start it so you can see. Let's start with my definition here. So we have our S equals. We're going to do this. Where we assume that any derivations in these x's here at t initial or t final are zero. So in other words, when we do these things, here's my s. It's just like when we did Lagrange's equations. We assume that right here. This is my delta x here. At ti is 0, for any of the components. This one here. 0. Okay.
We have class.
Yes.
And we have a unity different work.
Well, yeah, they already did it and handed them. They also took the first test.
The fuck of mine. Wait, is that actually a new thing?
Well, those are computational.
Ah,
So if you touch it, you have to do it now.
we'll do this.
Okay, what can we do with that derivative?
What do?
This is going to act like a derivative. Just like it did in calculus and classical mechanics. You can take it inside the integral and have it act down here. So we're going to have this. I'm just going to write this like that because it's just such a pain to write. Then what would this be? If there were a derivative acting on here, what would you do?
Change. Bird.
Okay, so you take the half down here. You take this argument and
Minus 1.
subtract 1 from the power, and then take the derivative of the anterior. So what this give you? This would give you 1/2. Okay, this thing to the minus 1/2 power. I'm just doing that for simplicity. Now times the derivative of the anterior. So this would be what? If I take the differential of the interior, so what do I get?
A triple product.
A triple product. So I get the variation in g mu nu. Okay, times dx mu d tau dx nu, this is set tau d tau plus g mu nu times this variation in dx mu d tau dx nu d tau plus g mu nu dx mu d tau variation dx nu d tau d tau. Now what can I do with that delta? You can just stick it inside this derivative field. Okay. So we're gonna beat on this next time, and there will be beating. And that expression is gonna come out. It will. Okay. There's gonna be some there's some heavy lifting to be done. Okay. And we're gonna get to cross off. We're gonna get what we're gonna end up with. Let me just jump to the end here. We're gonna find out. It's in the end. So in the end, we will show this guy here. Here, where? This is gonna be called the geodesic equation. And it's gonna be, it's one of the main equations that you have in general. We're gonna get a ton of mileage out of that. That equation will never go away. Okay. That'll be for tomorrow. Okay. And then if you get that, then we can, I'll start having you do things for you, so we do a lot of little 2x2 examples. As you can see, the general, this is gonna be, to calculate these things, is gonna be a little on the pleasure side. Okay. Okay, we're done. Oh,